Let's understand instruction cycle. There are three types of instructions: memory reference instructions, register reference instructions, and input-output instructions. The format of each type is shown in figures A through C. The 15th bit of a memory reference instruction, denoted by I, is the mode bit. If the mode bit is 0, it refers to direct addressing. A value of 1 refers to indirect addressing. With 3 bits of opcode denoted by bits 14 to 12, we get a total of 2 to the power of 3, that is 8 memory reference instructions. However, we use only opcodes 000 to 110, reserving 111 to differentiate memory reference instructions from register reference and input-output instructions. To differentiate between register reference and input-output instructions, we use the mode bit I, where 0 denotes register reference instruction and 1 denotes input-output instruction. A program is stored in memory and is made up of instructions. Executing a program involves executing every instruction one by one. To execute an instruction, we pass it through an instruction cycle. A program's execution will be completed once all instructions in the program are passed through the instruction cycle. As you can see, an instruction cycle is made up of 4 phases. The first phase is fetching an instruction from memory. The next one involves decoding the instruction so that you can find out what the instruction wants to perform or what kind of operations it wants to perform. The third phase is an optional phase which is executed if the instruction has an indirect address. And the fourth phase is that of executing the instruction itself. Now, what we'll do is we'll go through every phase of the instruction cycle one by one. So the first phase is fetching an instruction from memory. Now here what you can see are the micro statements, or let's say the micro instructions for the fetch phase. The fetch phase has mainly two micro instructions. Now these micro instructions are represented using register transfer language. So RTL refers to register transfer language, and we are representing every micro operation of the fetch phase using RTL statements. Now, what here you can see is here T0 denotes a clock cycle and T1 denotes the second clock cycle. So T0 is my first clock cycle and T1 denotes my second clock cycle. In the first clock cycle, what we do is in the fetch phase, we take the content of the program counter and store it in the address register. And in the second clock cycle, what we do is we take the content of the memory pointed to by address register and store it in the instruction register. That means the instruction which is present at memory location denoted by the value of address register is stored in my instruction register. And in the same timing signal of T1, we increment the program counter by 1. The next phase, which is the decode phase, involves a few operations, a few micro instructions, as you can see, and all these micro instructions, which are separated by commas, they are performed in one clock cycle itself. So in the first micro instruction involves decoding the instruction register. So what do? You decode bits 12 to 14. Now if you remember, here bits 12 to 14 represent the opcode portion. Bits 12 to 14, as you can see in figure A, that it represents the opcode portion. So if you are able to successfully decode what is present in bits 12 to 14 in the instruction register, then you will be able to find out the kind of operation that your instruction wants to execute. If it happens to be, if the instruction or if the opcode happens to be anything between 000 to 110, like we can see here, if the opcode ranges from 000 through 110, it will be interpreted as a memory reference instruction. If the opcode happens to be 111, that means if it has a decimal equivalent of 7. Now this 7 is denoted by D7, right? Now each of these numbers that you see D0 to D7, these represent the outputs of the decoder. So in order to decode the opcode, you'll obviously be using a decoder circuit. Now, how many bits are there in the opcode? There are 3 bits in the opcode. So in order to decode the opcode, you will be using a 3x8 decoder. So with 3 inputs, you get a possible of 8 outputs, where each output represents one opcode. Now, if the output happens to be, if the decoder's output happens to be 111, that means the D7 line, the D7 line of the decoder has been activated. And if D7 has been activated, it means that the instruction is either a register reference instruction or an input output instruction. And if the decoder output happens to be anything between 000 to 110, like we can see here, if it happens to be anything between 000 through 110, it is interpreted as a memory reference instruction. So that's how you will be able to find out whether the instruction is a memory reference instruction, a register reference instruction, or an input output instruction. Now, the 15th bit, if you notice, the 15th bit is denoted by the symbol I. Now, this is the indirect bit. Now, if the indirect bit contains 0, then it will be denoted as a register reference instruction, provided your opcode is 111. And if the indirect bit contains 1 and your opcode contains 111, then it will be denoted as an input output instruction. For opcode values ranging between 000 through 110, the indirect bit of 0 will represent a direct address instruction, and the indirect bit of 1 will represent an indirect address instruction. Now, after you're able to find out what the type of instruction is, whether it is direct or indirect, what you do is you take the bits 0 to 11. That means you take 12 bits of the instruction register, which denotes the address part, right? See, 0 to 11, this means there are 12 bits. So you take these 12 bits and you store it in the address register. What does the address register contain? The address register contains the address of the instruction which is about to be executed. So you place the address of the instruction in the address register, and what you do is the address part gives you the memory location in which you will have to go and find out the content. Okay, so you take the 12 bits of the instruction register, bits 0 to 11, and you place it in the address register. Now, using the value of the address register, those 12 bits, you go to your memory and fetch the value which is present there. You get the value which is present at that memory location denoted by the 12-bit address. Okay, now, and one more thing before I move on to the next slide, this I is a flip-flop. This 15th bit, the 15th bit of instruction register is stored in this variable I, and this variable I denotes a flip-flop. Okay, now moving on, for the indirect phase, what you simply do is, see, you take the, see, M of AR. M of AR means the memory location denoted by the value of AR. I'll repeat again. Here, this part, M of AR, M box brackets AR, this denotes the memory address given by the value of the address register. You take the content and you place it in AR itself, because it is an indirect instruction. Since it is an indirect instruction, first what you have to do, you have to first go to the memory location which is given by the address part of the instruction, and that memory location will give you not the operand, it will give you the address of the operand. So you have to make two references. So in order to make two references, you will have to first get the content of AR, the content of the address register, and find its memory location and place that value in address register, so that you can now get the operand in that location itself. So here, if you go through this statement, if D7 is 0, so if D7 is 0, it means that it is a memory reference instruction. And if I is 1, that means if the flip-flop bit I happens to be 1, it means that it is an indirect instruction. So with indirect addressing, what happens is the address of the operand is found by finding out the content of the memory location whose address is specified by the address register. So I'll just try to explain this. See, the address part, if it is an indirect instruction, then this bit, this I bit will contain 1. And the address part of the instruction will not denote the address of the operand, will not denote the address of the operand. See, if the indirect bit is 0, then the address part of the instruction will denote the address of the operand. If the indirect bit is 1, then the address part of the instruction will denote the memory location where you have to go and fetch the content of that memory location. The content that you fetch from your memory location will give you the address of the operand. So you have to make two memory references in order to get the operand. So remember, the effective address refers to the address in memory of the operand. So that is how the indirect phase works. Remember, the indirect phase is an optional phase and it is executed only if you have an indirect address instruction. If the flip-flop I bit is set to 1, it denotes that it is an indirect address instruction, and if that happens to be the case, then this indirect phase is executed. Now this diagram that you see, this represents the diagram for the fetch phase. So if you look at the fetch phase, the first thing that you need to do is you need to transfer the content of program counter to the address register. So how do you do that? In order to transfer the content of the program counter to the address register, you will have to you will have to have your select inputs as 0 1 0. Why 0 1 0? Because the decimal equivalent of 0 1 0 is 2, and if you observe that the program counter is connected to this common bus with a line connection of 2. That means whenever your select inputs will have a binary equivalent of this decimal value of 2, only then the content of the program counter will be placed on the common bus. So what we do is we set the select inputs equal to 0 1 0. As a result, the content of the program counter goes to the address bus. Next, we enable the load input of the address register, which allows the content of the common bus, which is nothing but the contents transferred from the program counter, to be placed in the address register. So that is how this part, this this part of T0 is executed. So I'll just repeat, the part of T0 is executed in two steps. Step number 1 is you set the select inputs equal to 0 1 0, which is the binary equivalent of 2, which will result in transferring the content of program counter to the common bus, followed by setting the load input of the address register, which allows the content of the common bus, which is nothing but the content of the program counter, to be transferred to the address register. So that is how you would execute this micro instruction, which is shown in timing T0. And for timing T1, what you do is, in order to execute these two micro instructions, you will see there is a connection between address register and the input of the memory unit. See, there is this line which connects the address register to the memory unit. Now, you simply enable the memory unit. So how do you do that? How do you enable the memory unit? See, if you observe carefully, what you have to do is, in this case, you will have to take the content of the memory and place it in instruction register. And if you remember, we have already placed the content of program counter in the address register. Now this M of AR refers to the memory location denoted by the value of AR. So how do you do that? You have to first enable the read input. You have to first enable the read input of the memory. That is the first thing that you need to do. In what I'm trying to show you here is the steps involved in executing the micro instructions against T1. The steps involved in executing the micro instructions against T1. So first thing that you need to do is you need to enable the read input of memory. That's the first thing. So by enabling the read input of the memory, the content of the memory unit will now be available for reading. Then what you do is you set the select inputs equal to 1 1 1. Why 1 1 1? Because if you observe, the memory unit is connected to the common bus. The output of the memory unit is connected to the common bus line of 7. That means if I have to transfer the content of the memory to my bus line, then I have to place a select input value, which is the binary equivalent of 7. And what is the binary equivalent of 7? 1 1 1. That is why what we do is First, we enable the read input of memory, and then we place the content of the memory onto the bus. We place the content of the memory unit onto the common bus by making S2, S1, S0 equal to 1, 1, 1. Now, after this, we transfer the content of the bus into the instruction register. Look at this. What you have to do? You have to transfer the content of the memory to the IR. IR here refers to the instruction register. So if you have to transfer it to the instruction register, you will have to enable the load input of the instruction register. So by enabling the load input of the instruction register, the content of the common bus, which is nothing but the content of the memory unit which we transferred, will now be stored in the instruction register. Now this will be followed by, if you observe, an increment in the value of the program counter. So program counter will be incremented by 1. And how do you do that? You increment the value of program counter by 1 by enabling the INR input. Here the INR input of the program counter will help you to increment the program counter, the content of the program counter by 1. And one thing you must have noticed is that there are multiple input OR gates. See, multiple input OR gates are included in the diagram because there are other control functions that will initiate similar operations that we talked about right now. So this diagram represents the register transfers for the fetch phase. Next, what you see here is the flowchart for instruction cycle. Now, what I'll do is I'll just try to explain this flowchart for you. So before going to the questions, let's just understand the flowchart. Now, it starts off, see, SC here refers to the sequence counter. Initially, the sequence counter has a value of 0. See, the first box, which is right on top, that is the starting point of your instruction execution. How do you start the instruction execution? You start it by setting the sequence counter equal to 0. Now the sequence counter will generate pulses. What are these pulses? These pulses are these values: T0, T1, T2, T3. These are the clock pulses which the sequence counter will generate. How will it generate? The decimal values which are placed in the sequence counter will generate equivalent timing signals. That means if I have a sequence counter value of 0, it will generate a timing signal of T0. If I have a sequence counter with value 1, it will generate a timing signal T1. If I have a sequence counter with value 2, it will generate a timing signal T2, and so on. So that is how you start things off. Now next what you do is, if you observe, it's in the next box. See, sequence counter has been set to 0. So the timing signal that it will generate is T0. And what will happen at T0? At T0, the content of the program counter will be transferred to address register. See, again, let me go back. See, in the fetch phase, so fetch phase is my first phase, and the first phase at T0, what do? I transfer the content of program counter to address register. And that is exactly what is shown here. The content of program counter goes into the address register. Now at T1, if you again observe, I had explained T1. In T1, two steps are involved. You transfer the content of the memory location denoted by address register to instruction register, and you increment the program counter by 1. So these two micro instructions are executed at time T1, and that is exactly what is shown here. Now at time T2, you perform the decoding operation. So how do you decode? You decode in multiple steps. The opcode part you decode using a decoder, a 3x8 decoder. Why a 3x8 decoder? Because 3 bits of opcode are used, and you get one of the 8 outputs if the output happens to be such that the last output line, that is D7, is activated. Then it would mean that it is either a register reference instruction or an input output instruction. See, that is what is shown here. You will have to check D7. Here D7 refers to the last output line or the 8th output line of the decoder. If the 8th output line of the decoder is enabled, what does it mean? It means that the binary value of this subscript 7, what is the binary value of the subscript 7? 111. So if that happens to be the case, if your output happens to be 111, it means that D7 has been activated. And if D7 has been activated, it means that your last output line of the decoder has been activated. And when will the last output line of a 3x8 decoder be activated? It will be activated when you have an input value of 111 for the opcode. So since the opcode is 111, if you remember, then Here, if the opcode is 111, it is either a register reference instruction or an input output instruction. So we have two options. If our D7 output is set, it will denote either a register reference or an input output. So we'll branch to the left. But if my D7 is 0, that means if the D7 has not been set, then either D0 to D6, any of the outputs ranging from D0 to D6 must have been set. So in that way, checking the D7 will give us the difference between a register or an input output and a memory reference. So if my D7 output is disabled, it would mean that it is a memory reference instruction. Now I'll have to check what kind of memory reference instruction it is. Is it using direct addressing or is it using indirect addressing? If it is using direct addressing, if you remember, then this indirect phase, like I told you, this indirect phase is optional, where you carry out this operation, this micro operation of transferring the content of the memory location denoted by address register to the address register itself. So this optional part is carried out if it is an indirect instruction. That is why you can see that at T3 this micro operation is present, whereas if it is a direct instruction at T3 you have nothing to do. And finally, what you do is you execute the memory reference instruction. So the last phase of the four phases of the instruction cycle. What is the last phase? The last phase is executing the instruction. So this last phase will be executed after you come to the conclusion that your memory reference instruction is either direct or indirect. So they'll both come to this box of execution, and after the execution is completed, you will simply set your sequence counter to 0 so that you can move on to fetching the next instruction. See, there is this big line which comes from here, from this right at the last box. From the end, you have a line going again back up at the top, where you again take the value of program counter and put it in address register. That means you will resume the execution of the next instruction. And what happens if D7 is 1? If D7 is 1, you come to this left branch where the indirect mode bit will decide whether it is an input output instruction or a register reference instruction. See, for a memory reference instruction, the indirect bit was responsible for deciding whether it was a direct memory reference or an indirect memory reference. But here, for register reference or input output, the indirect bit will differentiate between these two categories. So the indirect bit will differentiate between register reference and input output. So if the indirect bit happens to be 1, it will be considered an input output instruction. If the indirect bit happens to be 0, it will be considered a register reference instruction. So whichever is the case, at T3, you will simply execute your input output instruction, or you will execute your register reference instruction, and you will set the sequence counter to 0 so that the execution of the next instruction can begin. And before I conclude, I want to just say one more thing about this box T2. In T2, what you do is you also place the content of the instruction register. What is the content of the instruction register? The content of the instruction register of 12 bits starting from 0 to 11, you place it in the address register. This will give you the memory location from where you will be able to get your results, or not results actually, from where you will be able to get your effective address, or from where you will be able to get your operand. So in order to get the address of the operand, you make use of 12 bits of the instruction register. That's why here you can see 0 to 11 bits of the instruction register, which denotes the address part, is transferred in the address register. This happens to be the address part of the instruction, and that is stored in the address register. And this 15th bit of the instruction register is stored in the bit I, in the flip-flop I, which denotes whether it is an indirect address or a direct address in case of a memory reference instruction, or whether it is an input output instruction or a register reference instruction if your D7 happens to be 1. And concluding remarks would be that your IR is the instruction register, so it will hold the entire instruction. And here we assume that every instruction is of 16 bits. That's why the entire instruction is stored in the instruction register IR, and it is broken down into 3 parts, where each part is interpreted separately. The bits 12 to 14 will give you the opcode, the bits 0 to 12 will give you the address part, and the bit 15 will give you the mode bit. Okay, so these were the explanations as far as the instruction cycle was concerned. Now let's look at some prospective questions that may be asked. Now the first question is, what is an instruction execution cycle? So after explaining so much about instruction execution cycle, you probably would have understood how you can define an instruction execution cycle. I would still give you an informal definition. An instruction execution cycle can be defined as the phases through which every instruction has to pass in order for its completion. The next question is, we have been asked to describe the instruction execution cycle with the help of a diagram. So what you would do is you would draw this entire diagram and you would explain every box which is shown here. In this flowchart, every box that you see, you have to explain it, and you also have to explain the flow of execution, just like I mentioned in the earlier part of the video. And the third question you have, what are the different phases of an instruction cycle? So the different phases we saw, the different phases are these four phases. You'll have to write about these four phases where you have to fetch, decode, carry out an optional third phase if the effective address from memory happens to be an indirect address, and finally you have to execute the instruction. And the fourth question is, you have to explain the fetch cycle and indirect cycle using RTL. RTL stands for register transfer language. So here you have your fetch phase. So I've written down the RTL statement. So you have these micro operations. These micro operations for the fetch phase have been written using the RTL statement. So writing this part would be enough to answer question number 4. To answer question number 4, for fetch cycle, this portion which you see on your screen is enough. And if you were asked about the decode phase, writing the RTL statements for micro operations of the decode phase, then this part which you see on your screen right now, this slide would be enough. And similarly, for the indirect phase, if you're asked about RTL statements for micro operations of the indirect phase, then these statements which you see on your screen would be enough. Okay, so I hope this video proves to be of help to you. If you have any questions, please feel free to comment in the section given below. I'll see you in the next one.